All right, class. Welcome to the last week of lecture. That's an exciting thing, right? It means that our final exam is just around the bend next week. I need to reach out to the department to figure out exactly what the date, time, and location will be for the final exam. So that information will be forthcoming. I'll make an announcement on Canvas regarding all that info. Until then, you just need to be studying and completing all the assignments that are outstanding. As I made clear in an announcement, that all of those outstanding assignments will be due by the time that you are sitting down to the final exam. So no sooner, or I mean, no later than that moment. So you get out of the final exam and you realize you didn't finish a homework assignment, tough luck. I'm very sorry for you. I will have closed everything out at that point, and you will be held accountable for whatever it is that you actually turned in or didn't turn in. So that's a really very firm deadline for all of your assignments, and that last quiz that I left with no deadline as well. Since I lifted all the deadlines for all the assignments, I feel like this is a completely fair policy. You've had ample time to complete all these assignments, and so I really just don't have any sympathy for you if you fail to do so before the final exam. So I really don't want to get any emails from anyone asking for an extension, an exception, an exemption, anything. This is the firm and final word on the deadline for your assignments. Okay, so this week we are going to be devoted to reviewing chapter 11. As I also made clear in the announcement on Canvas, I decided to make the final exam non-cumulative or non-comprehensive, meaning you'll only be held accountable for the content from chapter 11, dealing with mathematical logic. I figured that will be challenging enough as is, and it'll make it easier for you to study and be successful, and means you don't, so you don't have to kind of get all of those old ideas back in your head and practice all of that old content. You can just focus on this new content, and I think that that will be sufficient. So I've prepared some review material. This is actually coming from the chapter 11 review in the back of the book, or in the back of the chapter of that book. So if you look into the end of chapter 11, there's a whole review section, and there's a assortment of questions that they've put together to help review the content. So I'm drawing these problems directly from that review, and the numbers here correspond directly to those numbers. So if you want to follow along or look back later, you have those numbers. Okay, so we're going to be doing a number of review sessions. So this isn't in any way a complete and exhaustive review in this one session. So bear that in mind. I'm just going to focus on some of the stuff that I think is particularly challenging for new students to logic. And that, to me, usually is when we're dealing with the purely symbolic logic. So all of the language, translating English into symbols and stuff, I'll do some of that in the review in a later session, but I wanted to focus on just the nitty-gritty, dealing with symbols and all these connectives and figuring out truth values. That's tends to be the most mathy part of this section, and therefore the more challenging. So we're looking at number 5. It asks us to determine which of these statements are tautologies. Remember what a tautology is. A tautology means that no matter what the truth values of the individual variables are in the complex statement, no matter their individual truth values, the whole statement will always be true. So you can change the values to true or false or true for various variables. And no matter how you change them, there is no combination of true and false for all the given variables that can render the entire statement false. So that's what we need to have for a tautology. So as we look at all these examples, we're thinking, is there any way for me to give a truth assignment to the given variables in such a way that I can render the whole statement false? Because if I can, then it's not a tautology. So let's look at letter A here. So this is P or not P. Okay, so solutions, and we're looking at A. So P or not P. So is this a tautology? Well, remember that in general, if we're just, I'm just going to choose two different variables to make this not confusing. So if we're just looking at an or statement in general between two variables, Q and R, then this statement is true as long as one or the other variable is true. So the one variable can be false and one variable can be true, but as long as at least one of them is true, then the whole statement is true, right? So just need one true. That's one thing you can think about it. Just need one true for an or statement. So we're looking at P and P or not P. We can think our way through this. We don't have to construct the truth table. And in fact, most of these, we can think our way through it without constructing a truth table. And that's usually the better route to go. Truth tables are time consuming, right? So P or not P. So let's think about it. If P is true, then not P is false. So we have a true or false. Well, that will still be true, right? Vice versa, if P is false, then not P is true. And we'll have false or true, which will still be true. So there's no way for me to get two falses out of this statement, because when P is true, not P is false, or when P is false, not P is true. So this must be a tautology. There's no way to render the whole or statement false. All right. Part B, we're looking at a biconditional this time. P implies Q if and only if, not P or Q, right? So this problem is really testing you on how closely you've been paying attention to everything that we've learned. And one of the things that we learned is that the implication is logically equivalent to not P or Q. These are the same thing. Remember what it means to be logically equivalent. That means that the biconditional statement with the different symbol, that means by definition that this is a tautology. So logical equivalence, which this symbol indicates, logical equivalence by definition means that if you replace the logical equivalence symbol, that double two-sided arrow, with just a single two-sided arrow, that this biconditional statement is always a tautology. So we must have that for logical equivalence. And so this second part is easy as long as we can invoke the fact that these two things are logically equivalent. Done. All right, let's look at C. So here we have P or not Q, if and only if, not P and Q. All right, so let's see what we can do with this. Now remember that for a biconditional statement, you get a truth value for the entire statement if both statements are either true at the same time or false at the same time. So that's the only way. Yeah, because remember, a biconditional can be written equivalently. Whoops, that should be not P and Q. So this statement is equivalent to the statement P implies Q and no, sorry. P implies Q implies not P and Q. And I'll put big brackets around that, a big and statement here. P implies Q implies not P and Q, and not P and Q implies P implies Q. So a biconditional can always be written as a big and statement with whose two statements are implications, right? So uniconditionals as opposed to biconditionals, if you like. So how do we make a conditional statement true? Well, a conditional statement like this is only true if both statements are true, the first statement is false and the second statement is true, or both statements are false. Similarly, we have to have either both statements be true here, both statements be false here, or the first statement be false and the second statement be true. Now, while we have the false true option for both uniconditionals, because there's an and statement, if we choose, for instance, false true here, then we'll end up having false true here, then we'll end up having true false here, and that would fail this truth assignment, this implication. So even though there is a way to have a mixed truth value in a conditional and get an overall true, you can't do it in this biconditional setting because that would force one of these bigger statements to be false. So the moral of the story is the only way that a biconditional ends up being true is if you have true if and only true, or you have false if and only false. So those are the two things that would need to happen. So we'll bear that in mind. That's one strategy, is that we just need to think about, is there any way to make this one true and this one false, or this one true and this one false? And if there is, then we do not have a tautology. And if there isn't, then we do. So I'm going to flip to the back of this page and rewrite this. P implies Q if and only if, not P, was it or Q, and Q. And Q. All right. So let's just game it out. We don't have to really do a truth table here. So the ways that the first statement can be true are P is true, Q is true, or P is false, Q is false, or finally, P is false, Q is true. So these are the three ways that you can get a true statement here. So we want to see that for those three ways, we get a true here. Do we always get a true here? So what happens? So if you have a true, true, then you'll have a false and true, which will ultimately be false, but then you negate that, so you get a true. So this one works. You get a true here and a true here. Okay, let's look at this one. So false, false for P and false for Q. So if P is false, then not P is true, but then Q is false. So that means the and statement is false here, but then it's negated, so it becomes true. That works. And then we have false true. So that would make P, not P true and Q true, rut row, which would mean the and statement would be true, but then we negate the and statement, and that becomes false. So that fails. So we've therefore shown an instance where a truth assignment for P and Q renders this side true, while at the same time it renders this side false. And that means that since a biconditional can be thought of as this direction and that direction at the same time, while false implies true is good, true implies false is not good. So this therefore shows that this is not a tautology. So again, if it's hard for you to follow the way that I'm thinking through these problems, you can always construct truth tables to think your way systematically through a logical statement. It behooves you to learn how to think otherwise, because then you waste less time. Drawing up truth tables, that you end up considering a lot of cases that immediately don't work. So for me, I just thought, here are the 3 cases that I know will fit this statement. Let's just see what happens when we apply them to this statement. So I was able to reduce the amount of things that I needed to think about by approaching it this way. But you always have the option to construct a truth table if that appeals more to you. Okay. All right. We had one more on this problem. So D, P implies Q implies R if and only if P implies Q implies R. Okay, so this one should be an easy one, because we know that according to the, I forget exactly what they called it, maybe logical precedence, or the precedence of certain connectives, you know that the implication symbol is at the same level of precedence. And what that means is that we can draw parentheses any way we like, and it doesn't change the statement. So ultimately, P implies parentheses Q implies R is the same as parentheses P implies Q implies R. So really, you can write this without any parentheses whatsoever. And you would see that clearly, once you remove the parentheses from both statements, you have the same exact statement. So the biconditional will obviously be true, since they're the same thing. That's clearly a tautology. So we're done. So it looks like it's going to be bad, but because we know about logical precedence and the precedence of various connectives, the implication symbol clearly has the same level of precedence as itself. So that means you're going to wrap parentheses in different, you can write the parentheses in different places and not change the overall truth value of the statement. Okay, so that's number 5. Let's look at number 6. So here we're just being asked to construct truth tables. So I thought I'd go over this once again, just for completeness. Hopefully this has become an old hat for y'all, constructing truth tables, but let's go ahead and do it. So part A, we're looking at P implies not Q or R. Okay, so we're going to draw up a truth table. It's going to require a P column, a Q column, and an R column. Okay, now remember I told you how to figure out how many rows you're going to need. You take the number 2 and you raise it to the power of the number of variables. So there are 3 variables here, P, Q, R. So 2 to the 3 is 8. So you know you'll have 8 rows. So once you know the number of, you just, for the first P, you divide it in 2. So 4 truths and 4 falses. For the Q, you divide that in 2. So 2 truths, 2 falses, 2 truths, 2 falses. And then for the R, we just alternate. True, false, true, false, true, false, true, false. And so by doing it in that pattern, remember what you've essentially done is come up with every possible combination of true and false for the 3 variables. Okay. So now what we'll do is we will write the whole statement kind of big so that we can kind of consolidate the truth table. So essentially what we'll do is think about this column is representing the implication. We can have this column represent the not Q, and we could have the final column represent the or statement. Okay, so let's do this. So we have to work our way inside out. So we start inside the parentheses over here, and we have to deal with the not Q. So for not Q, we just flip the truth assignments around. So that's false, false. There's my green pen going. True, true. False, false. True, true. Yep. So that's all the assignments for not Q. Now we deal with the or statement because we already have R over here, so we didn't need to give R its own column. So now we're just comparing not Q or R, and all we need in order for that whole statement to be true is to have at least one true. So true or false gives us a true. Sorry, false here. False, false or false gives us a false. Gotta get it right. There we go. True or true gives us a true. False or true gives us a true. Right, 1, 1, 2, 3, 4, 5. Yep, and then 1, 2, 3, 4, 5. So true or false gives us a true. False or false gives us a false. True or true gives us a true. And then finally, false or true gives us a true as well. Okay, so let's make sure we got 8. 1, 2, 3, 4, 5, 6, 7, 8. Very good. Okay, so finally, we're going to deal with the implication, which is on the outermost connective for this logical statement. And this is ultimately the column that we're concerned with, right? So what is the truth value for this column? So we're doing an implication between P and this whole statement. And the truth values for this statement are here. So we're comparing this column with the P column. And for an implication to be true, it's either true implies true, false implies true, or false implies false. Right, so let's take a look. We've got true implies true. That's a true. We've got true implies false. That's a false. We have true implies true. That's a true. We have 1, 2, 3, 4. 1, 2, 3, 4. Yep. True implies true again. So that is a true. We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. False implies true. That is a true. False implies false. That is a true. False implies true. That is a true. And then another false implies true. That is a true. Let's make sure I didn't do too many. 1, 2, 3, 4, 5, 6, 7, 8. Great. All right, so we've constructed the truth table. The ultimate values that we're interested in lie in this column for the big implication. You can see we almost have a tautology except for this row right here where we get a false. Okay, so we'll do another one here. I have to do this on the back of this page. Let me copy it down. P and Q if and only if R and P. So P and, bear with me, Q if and only if, Q if and only if R and P. I think that's what I read. Let me read it one more time. R and P, yep, okay. So we're constructing a truth table for this, all right? So yet again, we have 3 variables. So we know how to construct this truth table. P, Q, R, true, 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 false, 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 true, true, false, false, true, true, false, false, true, false, true, false, true, false, true, false. All right, we've set the stage. Now we'll do just like I did before. We'll write the whole statement real big and then use separate columns to sort of represent the various connectives. So P and Q if and only if R and P. Okay. So what do we need? We need a column for the big and here. We need a column for the if and only if. And we need a column for the and statement. We work from the inside out, right? So we'll first figure out the and statement, then we'll figure out the biconditional, and then finally the big and on the outside. Okay, so we have and statement between R, P, and R. So and statements are only true when both are true and are otherwise false. So we're just looking for 2 trues, otherwise it's false. So 2 trues gives us a true. True false gives us a false. True true gives us a true. True false gives us a false. False true gives us a false. False false gives us a false. False true gives us a false. And false false gives us a false. Okay, check it. 1, 2, 3, 4, 5, 6, 7, 8. We're good. Okay, so now we've done the interior-most and statement. Now we're moving one layer out to this biconditional. This biconditional is between Q and everything in this column, right? So we're going to compare Q with this column. We have a biconditional. That means in order for the biconditional to be true, we either have true, true, or false, false. There's no other way. All right, so true, true here gives us a true. True, false gives us a false. False, true gives us a false. False, false gives us a true. True, false gives us a false. True, false gives us a false. False, false gives us a true. And false, false gives us a true. Okay, let's check it. 1, 2, 3, 4, 5, 6, 7, 8. All right. So now we've dealt with the biconditional here. So finally, we're moving out to this and. We're going to compare P with this whole statement, which is coming from this column. We have an and statement, which means we need 2 trues. Otherwise, it's false. Okay, so true, true gives us a true. True, false gives us a false. Now, honestly, we can do this quickly, right? Since it's an and statement, we need all trues. So if we just look in either column for where the falses are, we can assign all falses for those. So immediately I can see false, there's going to be a false there. There'll be a false here and a false there. So the only places we could possibly have trues are where there's trues over here. And so we just need to check those. So that's the 4th one down. We got 2 trues. So that's a true. And then the 7th one down, we got a false over here, so no dice. And we got a false over here on the 8th one, so also no dice. That's 1, 2, 3, 4, 5, 6, 7, 8. Good. Okay. And so that is the final column. That's the result of the statement of the truth table. And this is clearly not a tautology, far from it. It's usually false, sometimes true. Okay. So that's truth tables. The more you do them, the more practice you get, the easier they are. Writing it out this way with the big statement and giving columns to the various connectives is honestly one of the most efficient ways to do this, and I highly recommend you wrap your head around that. Okay. Okay, so the last problem I wanted to go over was for this particular review session was number 7. And here we're given 2 statements, and we want to see if they are true or false. Now, notice that they've put in the logical implication symbol here. And so remember what that means. That the only way that this statement is true is if when we replace this logical implication symbol just with the implication symbol, that must be a tautology. So let's check it out. Solution, part A. We're looking at P and not P or Q implies Q. So what we need to see is if this statement, where I replace that with the implication symbol, is this a tautology? If it is, then this statement is true. So to be a tautology in this case, what does that mean? Well, the outermost connective is this implication symbol. And in order for an implication to be true, you need one of 3 things to happen. You can either have true implies true. You can have false implies true. Or you can have false implies false. So that's the way that this thing will ultimately be true. So each of these will equal true. So what we really need to see is that, is there any way to get these are the 3 ways that we can get a true which means there's one way to get a false, and that is when we start with a true and we imply a false. That equals false. So in order for this to be tautology, there should be no way for this to happen, right? So we want to focus on that one, really. If we can, if there is some way to make this happen, then we show clearly that this is not a tautology. Just by showing that these three can happen doesn't mean that this one won't happen, right? So we really just need to eliminate this one, and then the only other options are the remaining three, so we're good to go. So let's see what we can do. So looking at this statement, P and not P or Q. Okay, well, one thing that we can do immediately with this is use the fact that for this or statement, we know that that or statement is logically equivalent to P implies Q, right? So what has to happen for this statement to be true? We need the and statement to be true, which means we need to have a true and true. So in order for it to have a true and true, that means P must be true. And so if P must be true, then the only way for this implication here to be true is Q must also be true. Right, so we're kind of working our way through a proof, and I'm just doing it more kind of as I go. But you know, the proof would basically go. We can say not P or Q is logically equivalent to P implies Q. Since that's true, we can clearly see that in order for this big and statement to be true, P must be true. So we can assert the truth of P. If P is true, then in order for P implies Q to be true, Q must also be true. So we can assert the truth of Q. So what have we actually figured out? We figured out that in order for the first statement in its entirety to be true, Q must be true, always. And so what do we see? We see that there is no way for this statement to be true and this other side of the implication to be false. There's no way to get this fourth result. Because if this is true, then Q is always true. So we always have a true implies true. And that's all we really needed to show. There's no way for this to happen. If there's no way for this to happen, then this has to be a tautology. And that means that the statement up here, the logical implication, is true. So if the simple implication is a tautology, then the logical implication is true. There you go. Okay. So this one, again, not doing truth tables, just trying to think about this sort of strategically. You think about the big statement, and how can that big statement ever be false? That big statement is only false when you have a true implies false. So you then see what happens when you force the first statement to be true. Is there any way to get a false on the second statement? And what we saw is that once we force the first statement to be true, it in turn forces the second statement to be true, which was just Q. And once you have that, then you know that there's no way to get this certain combination, true implies false. And that's the only way that this big statement over here is ever false. So it must always be true. Therefore, it is a tautology. Therefore, the logical implication is true. So that's the whole way that we think our way through this. Again, if that is too befuddling for you, you can always form a truth table and work your way to that same conclusion. It will just take a lot longer. Okay, So now let's look at the second statement here. I'm going to write that on the back. Give me a second. So we got P implies Q, or Q implies P. P implies Q, or Q. No, and Q. And Q is logically implies P. Okay, so we're going to think our way through this again. We have this logical implication. So the only way that this logical implication, when we rewrite it as a simple implication, the only way this simple implication is ever false is if we start with a true and we get to a false. So let's check that out. How do we force this to be true? All right, so we need P implies Q and Q to be true. We want it to be true. In order for that to be true, we need true and true. So notice what happens. When we need true and true, we're forcing the Q to be true. If we're forcing the Q to be true, then what does that mean about P? Well, we need this implication here to be true, and implications are true when either you've got true implies true, false implies true, or false implies false. So notice what's happened here. In order for this big statement to be true, Q must be true. Once we know Q is true, what are the ways that this P implies Q could be true? Well, it turns out that just because Q is true, we can eliminate this option because we know Q must be true. So the only way that Q can be true, there are two ways for Q to be true and P to have different values, and this whole thing still equal true, right? So what do we see? We see that even though Q is forced to be true, P is not forced to be true. And that means that ultimately there's a way for this thing to be true and this thing to be false, rendering the whole thing false. If we write it like a proof, we'd say, okay, what's the first thing we can assert? We can assert that if we assume this is true, then Q must be true. If Q is true, then in order for P implies Q to be true, P must be true or false. So actually, there is no limitation on P. So that means there's a way that we can select P to be false and still get a true statement here, which would mean that here we would have true implies false. And that would render this whole thing false, which then renders this logical implication false. So sorry for the beating. My wife is doing something in there. Yeah. I don't know what she was knocking on, but we'll keep it in a cloud of mystery. Anyways, so we see that there is a way for us to get a true implies false, and therefore there is a way for this whole big implication to fail. And so it is not a tautology, therefore it is a false statement. False in the sense that it is not a tautology, not false in the sense that there isn't some way for it to be true. There are ways for it to be true, but because there are also ways for it to be false, it is not a tautology. And we need tautology in order for this symbol to hold. Okay, So that's going to conclude the review for today. I will post the review on Wednesday and very likely on Friday if I feel like there's more to review. And the details for the final will be forthcoming. I'll make an announcement on Canvas. So study, and get all your assignments finished up before the final, and you should be in good shape. All right.